Assalamualaikum warahmatullahi wabarakatuh. Good morning. First of all, let me introduce myself. My name is Harti Maulana Hermawan and my partner Karil Edo Hirmasya. We are from Group 4. We will present our high-rise building project with the title Petronas Twin Tower. Without further ado, let's get started. Okay, first, introduction. Petronas Twin Towers, or in Malay is called Menara Kembar. Petronas are twin skyscrapers in concourse level, lower ground, Kuala Lumpur, Malaysia. They were the tallest buildings in the world from 1998 to 2004. The Petronas Towers remain the tallest twin towers in the world. Although the Petronas Tower is no longer the tallest tower, but for now, it is still the tallest twin tower in the world. As you can see, in the first place, Petronas Twin Towers Kuala Lumpur with the 451 meter, and number 2 Marriott Marquis in Dubai, and for the last Grand Gateway Shanghai. Okay, next, milestone. The Petronas Tower start of project planning at January 1992. Then in March 93, start of foundation work, and at April 94, construction of the superstructure, fitting out the interiors complete with furniture at January 96, and the March 96, taking off the spires of the Tower 1 and Tower 2. January 97, moving in the first batch of Petronas personnel, and then the last August 98, official opening by Dr. Mahathir Mohamad as a Perdana Menteri of Malaysia. Okay, for building Petronas Tower, many person and many part include here. Companies involved, especially owner of or developer KLCC Property Holdings Berhad, and architect Cesar Pelli and Associates, structural engineer Thornton Tomasetti, MEP engineer WSP Flag and Kurtz, project manager Landis, main contractor Hazama Corporation for Tower 1 and Samsung Engineering for Tower 2, and many other like a consultant dumping, facade maintenance, fire and wine, then material supplier construction hoist, elevator, facade maintenance equip, paint or coating, sealants and steel. Okay, over, this is an overview for Petronas Twin Towers building. Exterior. This is Tower 1, Sky Bridge, and Tower 2. In interior, very luxurious. And this pinnacle, Tower 1 and Tower 2 have the same pinnacle. Okay, next, the Sky Bridge. The Sky Bridge have the elevation at 41 and 42 floors. And for the open this Sky Bridge, you need a sound ticket. Area, size, and dimension. Number of storage is 88 with the 5 floors below ground. Height from ground to tip 452 meter, or you can say 1483. The Petronas Tower have a 395,000 units square meter built-up area with 213 unit square meter free space for use and 186,000 unit square meter annexes for a foundation, 120, or you can see, or you can say 400 feet deep under the ground. Okay, next, why do we choose Petronas Twin Towers? The first reason is because the Petronas Twin Towers were once the tallest buildings in the world. In 98 to 2004, located in Southeast Asia, where most of existing countries are developing countries. The reason number two is Petronas towers have different contractor between Tower 1 and Tower 2. Okay, next, for the structural system of Petronas Twin Towers will be presented by my partner, Karil Edu Hermans.
Okay, firstly, about I will explain about foundation structure. The geotechnical survey discovered that the actual construction site was situated partially over decayed limestone deposition and rest over soft rock. After discovering this, the structure was relocated to avoid limestone deposition. The whole foundation was rested on 104 piles. To reach safe bedrock, the piles were extended to depth ranging from 200 until 374 feet. To reach this depth, Petronas Tower became the structure having the deepest foundation of the world. And the next, about foundation structure, at the picture we can see about foundation plan and foundation issue. The piles were embedded by thick raft. This raft was 15 feet in depth and it requires enormous amount of concrete to cast it. This is about 4,470,000 cubic feet, which was the large continuously poured concrete until 27. This huge quantity of concreting for each tower required 54 hours to pour. Okay, next. The system structure. The structural system of each tower comprises a 25 meters and 50, 25 meters central core and an outer ring of widely spaced 16 cylindrical super columns. At the beside of the text, we can see about the picture. At the first, we can see about beam, basal column, and under is main column and core. First big demonstrate 16 cylindrical columns are constructed using high-strength reinforced concrete. These columns are linked by ring beams to build a moment frame other tube. This is one of the good explains of tube-in-tube system, as there as a pair of soft tubes. Second peaks represent the tube-in-tube structure system for Petronas Tower, with the inner core and the outer tube shown separately. Okay, next. Uh, this is about wall structure. You can see on the picture about reinforced concrete, aluminum composite panel, glass face, and UPL hips. The Petronas towers feature a diamond facade consisting of 80, 80 30 500,000 square meters of stainless steel extrusions. In addition, a 33,000 panel curtain wall cladding system resides within the tower, while the stainless steel element of the towers entice the illustration sound, highlighting the magnificent tower. They are, they are composed of 55 square meters of 20-38 millimeters or 0.0.82 inch laminated glass to reduce heat by reflecting harmful UV rays. And we can see about the wall structure, the foundation of wrap all hips from, and then additional shape, combination shape. And we can see about combination shape from gravity loads. Geometry is used as the main concept of the structural and design of Petronas Twin Tower. Next, um, there are four pictures represent about load distribution directly. Second picture about diagrams here, and third lateral diagram, and fourth bending moment diagram. At the sky bridge, the structural system of sky bridge is double deck bridge spanning 5 58.4 meters, connected to tower at Sky Lobby Elevators Transfer Station. It is third on the floor 40, 41 and 42, and then easy circulation by per we upper tower floors and minimize light usage, reduce fire exit requirement, grid height and span, requires steel for lightweight and easy cons. To hike art super to span, self-centering action from airtime at arts, and crowned at spherical pin at support. And the next at the sky bridge, you can see the representing of the structure of moving section in plus 1 meters and tempered device inside legs. At the center, we can see about bearings tube and at the foot, bright red in 63-degree tilt and at really the bottom of the foot, two steel tubes and at the floor 28 until 29. The sky bridge building the two towers used the combination of rectangle and triangle structure to add strength and stability to the bridge. Next, on the roof structure, um, air at the pinnacle structure, the upper building of the Petronas Twin Towers, we can see the first big, the air terminal lighting protection, and then diagonal column, structured steel, and machine maintenance. At the second peak, concrete profile, glass facade, and then the roof used a lot of triangular shaped structure to give a better support to the building. Next, in the pinnacle structure, in the analyzing modeling, the firstly 3D modeling using SAP 90, and the second including perimeter beams, columns, central columns representing core and outrigger system, and the third column cross section properties use compressive strength dominant, elastic moduli E values varied with strength according to AC 318 and the E value not reduced for Gibson's terms. Next, and the next I will continue the project 3. My title is Substructure of Petronas Twin Tower. The first about soil and bedrock conditions. A generalized soil and bedrock profile below the tower is shown in Figure I. The geologist profile consists of 12 to 20 meters of medium-dense, silty and clay alluvial sand. The alluvium is underlined by a medium-dense to extremely dense, sandy and gravelly silt and clay materials which residual soil and withered rock deposit now locally and the Knight Foundation. The bedrock below the Knight is of Silurian age and consists mainly of calcite and dolomitic limestone and marble. The rock surface is very irregular and has been weathered by solution activity creating numerous joints and cavities. As a result of the solution activity, isolate zones of the canal hill have eroded into the bedrock cavities creating soft or losing zones referred to as slump zones. The hard canal hill above arch over these slump zones they don't feel the full weight of the overlying formation. For design purposes, the slump zones were defined as nihil just above bedrock with standard penetration resistance or N values less than 20 blows per 30 centimeters or 20 blows per foot. By these definitions, six slump zones were identified beneath the footprint of Tower 2 and known below Tower 1. Guinea Hill Formation and is, is 20,300,000 figured limestone bedrock rock 0 until 100 feet. One tower found foundation profile scale 178 76. The rock surface steps steeply from northwest to southeast such that the tower pulleys are situated over bedrock located 90 to 80 to 90 meters below trade grade. The towers themselves are situated with rock at 100 to 100 meters below street grade, as shown in Figure 1. There is also a valley feature in the bedrock surface between the tower extending deeper than 200 meters or 6, 6, 658 feet. Okay, next. The firstly about irregular bedrock beneath site, and the second on the first peak, perimeter diagram walls 2 inch from 6 thick. The underground forest of fracing piles, providing greater distribution of the tower's weight solution. Two rough foundation 5 thick containing three 13 com of concrete. There are 300,000 metric tons of eight towers spread over concrete slab or made anchored to solid not bedrock. The towers rest on RCC foundation made poured over piles. 208 vertically piles rectangular 9 feet and 4 feet and 197 feet to 380 feet control setting. Next, about foundation requirements. Due to the height slenders at the structural interconnection of the towers, the developer and the designer aimed for a differential settlement as close to zero as practical. With the anticipated geology of the goal of minimizing differential settlement, foundation alternatives to this include a floating raft, a system of bird piles, sockets, immune to limestone below any significant cavities, and a raft on Frisian piles located in the canal hill below above limestone will pile lengths vary to minimize differential settlement. The large size and grid strength and safety requirements of the floating raft preclude its use. The grid depth to the bedrock made such board piles impractical. Therefore, the friction pile six scheme was used. During the preliminary design and soil exploration phase, it was found that the bedrock elevation at the initial tower location varied so greatly that rock actually protruded into the proposed basement on one side the tower. This made control of differential settlement impractical. The tower's location were then shifted approximately 90 meters to where the tightness of the Knehill foundation was sufficient to support a raft on board friction piles. There, the required differential settlement limitations could be achieved by varying the length of pile of barracks. Next, on the exploration requirements, the exploration program consists of one of more than 2,000 borings and 200 probes on 8 meters, in addition to 260 in situ pressurometers tests and two fully intrums 350 tons pile load tests were performed to define the modulus properties of the supporting Knehill formation. The soil properties summary and the pressurement test summary are shown in tables 1 and tables 3 from reference 1. A representative standard of penetration-resistant profile is shown in Figure 1. The load tests were of the knowledge that load reacting type with high blocks of concrete providing the reaction to assure maximum side friction. The spile TP1 was passed through maintain type scan growth. Tubes acted to the repair case. Okay, next. The explain before, this is two picture represent about the soil substructure of foundation in Petronas Twins Tower. Okay, next. This is two the settlement analysis and assumptions. Extent settlement analysis were performed utilizing the SAP 90 program and the Places Axis Symmetry program using soil modulus estimated based on back calculation for the test file program and from averaging the rebound modulus slope of these in situ experiments tests. Pile lengths were varied until calculate maximum differential settlement goal were achieved based on bearing capacity consideration only. Barrage lengths of 33 meters would have been sufficient to support the design loads, but pile lengths under the main towers varies from 40 meters to 105 meters based on settlement consideration. Figure 4 shows the predicted settlement and ground deformation for the final design. The case using figure 5 and 16 from reference. Okay, next. This is the, yeah. And the next, Barrett's Foundation 1.2 and the Barrett's Foundation 1.2 meters by 2.8 meters and 0.8 2.8 meters in sections for the towers and bulkheads representatively were installed for the initial partial excavation level of mean 4 meters below grade to depths varying from 18 from 60 meters to 130 meters below grade, utilizing slurry trench cutting machine of the hydrophrise type with counter-rotating cutting wheels for the deeper foundation. The cutting mix with bentonite slurry were pumped to a designing plant for regeneration and eventual recycling to the barrage shaft by installing the barrage prior to the major basement excavation to mean 25 meters. The barrage acts to resize soil health, the structuring and softening of the Canal Formation when the basement excavation was made. A 4.5-meter thick mat was constructed on the top of the barrage to transfer load from the core and perimeter columns to the barrage. Okay, next. The instrumental program. This is therefore load distribution curve compute from SGS measurement, and the seconds represent the T145A or SIGI. Next, it's same with the slide of before. The foundation structure, the data available from the instrumentation program for both tower is immense and will be studied and reported on the due time by the local geotechnical engineers. The selective data represent here for Tower 1 provides a preliminary picture of the general result. A very high percent of the installed instrumentation work consistently throughout the construction. The data overlay on the train cake reading is complete through early spring 19, 1997 when the full load of the building was in place. The pressure cell information is only available through contraction up to about the 35 level with less than half the full building loads in place. Okay, next. Okay, next. It's same. This is uh, before, please. At the performance evaluation, predict maximum settlement for the complete tower was 73 millimeters, with maximum differential across the match of 12 millimeters. Based on the settlement measurement taken during construction, it appears that both measured total and differential settlement of the tower are less than predicted, indication that the goals of the depth ground improvement program were met. Okay, next. This is and then it should be noted that the part of the report differential settlement is suspect, since the major portion was reported immediately after pouring the concrete mat before a significant additional load had been applied. This the level of reading reliability may be on the order of 2 to 3 millimeters. The strain gauge data from the barrage indicates considerable variation in how the load is transferred down the barrage, indicating the variable nature of the Kenny Hill formation. In some of the barrage, all the load is transferred in friction with no load, reaching the tip or low strain gauge level. However, in other parades, significant load rates the type even when the parade as long as 65 meters. Maximum developed friction along the pile varied uh, 63, 73 kilopascal to 260 kPa. This is consistent with the test pile program where maximum developed friction rates over 300 kPa with no signs of slippage. It should be note that even is two spirits where some loads increasing the type, the major portion of each New load is still being carried in friction. Next. Okay, next. I think enough for me, and then we'll continue by my partner of Hardy.
Okay, I will explain about okay, I will explain about upper structure of Petronas Twin Tower. Upper structure. Upper structure or superstructure is everything that is above ground. This area includes the first and second floors inside a home and any number of floors in larger buildings. The superstructure includes beams, columns, fins, windows, doors, a roof, floors, and anything else. The first, pinnacle, its tower crowned by minus 73-meter pebbling top, accommodates building maintenance machine, aviation lighting and lightning protection. Due to steep sloping column, concrete construction in vertical and steel used throughout. Okay, pinnacle. Mm, like my partner explanation, this is air terminal lining protection, and this is diagonal column, and this order is in this order, or this structure is formed by steel, and then inside here there is a machine maintenance. In this structure use concrete profile, and this structure use glass facade. And this MEP or picture pinnacle elevation. Okay, next for a wall structure, the Petronas Twin Towers is mostly built by concrete profile. This is a reinforced concrete. Is useful for a strength of Petronas Twin Tower, and in outside wall or window, Petronas Twin Towers using aluminum composite panel, and in the bottom of window using glass facade, and for the shape is used UV alkyds. Okay, next for the floor. The floor planning design was originated from the ancient Islamic forms of eight-pointed stars and decorative motif. When viewed is plan, the towers appear as row overlapping squares interlocking heaven and earth to create an eight-pointed star which is further refined with half circle between the star points. This is the concept and structure. The support beam, perimeter column, bastel, and the core. Column. Column cast in reusable steel forms, finely finished columns open to view at most of the floor. Concrete varied from M80 to M30 in three steps. 12 bastel columns, 1 4 meter to 1 meter. Setbacks at 60, 9, 73 and 82, sloping columns over 3-story heights above floor, 84 steel column used to avoid complication. Beams, tapered ring beams all around, depth 115 meter at column to 725 millimeter at flat zone, span variation due to column change and setbacks. Beam grade meets column grade to simplify palming. Okay, for the next is bridge structure. Engineering design the structural system selected utilizes a two-hing arch, springing from supports at level 20, 29 and rising at 63 degrees to support a pair of parallel two-span continuous bridge girders at level 41. The structure of the two-level bridge, conventional framing constructed of structural steel with beams mounted connected to columns which bear on the level 41 continuous girders. The Sky Bridge was fabricated and sub-assembled by Samsung Heavy Industries of South Korea to facilitate putting it into place. The Sky Bridge was pre-assembled into five main components, comprising the two legs, two end blocks, and the center section. For bringing the Sky Bridge up, there are 9 steps. Step 1 is the sky bridge legs are lifted up one at a time by tower cranes. Once they are in position, control cables are used to lower them over their permanent bearings at level 29. And for your information, the crane is placed in tower 2. Step 2. The two and block girder frames of the skybridge are lifted individually. The blocks are installed about 100 millimeters above their final position at level 41. They are also retracted about 100 millimeters into the tower to provide sufficient clearance for the skybridge center section during lift. Step 3. The four lifting jacks located at level 50 of both towers are connected on bridge center. The other four lifting jacks located at level 48 of both towers are connected to the bridge ends. Step 4. The center section, which weighs 3,125 tons, is lifted about 11 meters and restrained. This is to allow the upper 10 meters of the legs to be connected to the girder on the bridge. Step 5. After a final check, lifting on the center section commences. And step 6. At the minimum lifting speed of 12 meters per hour, the center section is gradually lifted to its final level in floor 41 or 50 or 42. Step 7. Step 7 to 9 took about 2 weeks. A temporary connection secures together the center section and the end block girder frame to ensure there is no stress. The legs are moved into place. When the legs are in their final position, the sky bridge and blocks are lowered on their permanent bearing at level 41. The center section is then lowered to meet the legs. So center section is bring to lower to connected with the legs, the two legs. 5 minutes after the lifting system has been removed, the floors were concrete, the skybridge roof, the maintenance equipment is set up on stainless steel rests on top of the bridge. At about 7:40 p.m. on 9 August 1995, after 32 hours of lifting operation, the skybridge was lifted to its final position at the 41st and 42nd floor of the Petronas Twin Tower. Okay, that's all my group presentation. My name is Ardi and my partner Karil Edu Hermansyah. Thank you for your kind attention. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.